Welcome back to this week's algebraic graph theory seminar. This week we have Klas Markström talking about guessing numbers of random graphs with low minrank.
Oh, thank you, and hello to everyone. I guess this is again one of these occasions where we end up speaking to you from the very northern end of the world. So moved Sabrina up here too now. So I'm going to be talking about something that really is, well, I was asked to talk in this seminar series, and it's called the seminar series on algebraic graph theory. So I thought I'd better talk about something that has some algebraic content in it rather than just graph theory. So I decided to go back and look at one of all of these research projects that, well, got started up and then stopped by the pandemic. So this is joint work with Demetres Christofides, who is at Cyprus nowadays. And based on something we started discussing a little bit before the pandemic, and then the pandemic hit and other kinds of stuff got done for a while. So this was a good way of kicking myself into actually aiming to write this up as a paper. So what's this all about? Let's see. I need to be there. So the background for the problems that I'm going to talk about is a bunch of equivalent things. One part of it connects to something called network coding that some of you may or may not have heard of. The other one is a guessing game, and that's the main thing I'm going to mention. It's also equivalent to a certain design problem for Boolean circuits in terms of constructing optimal circuits for certain Boolean functions. And this guessing game that I'll soon describe was introduced by certain Riis at Queen Mary University in London in order to, primarily his motivation from the beginning was this, an open problem on Boolean circuits by Leslie Valiant that he could give a negative answer to using this. To this list of equivalent stuff has more recently also been added something called storage codes, which again turns out to be equivalent to all of this. So in Riis guessing game, we have n players. And before the game starts, the players can discuss, they can come up with a strategy and do whatever they like. But as soon as the game begins, the communication is going to become impossible. So you cannot come up with anything that's communications based if you're going to do something here. So then what's the game about? Well, when the game starts, each player will get a hat. And it's going to be red or green, and they are going to be chosen randomly. And they have a broad brim, so you can see everybody else's hat, but not your own. So you don't know what color your own hat has, but you know everybody else's color. Next, each player needs to write down a guess for the color of their own hat. And you're thinking that I don't have any information about my own hat, and that's quite correct. And finally, all those written down guesses are revealed, and the team wins if everybody guessed correctly. So as soon as anyone is wrong, this is all a loss. And then, well, what can you do here? How large can you actually make the probability of winning in this game? And obviously, if everyone just guesses completely at random, then you have a 50% chance of being correct about your own hat, and we get 1/2 to power n. And I have absolutely no information about my own hat, so we certainly can't win with probability more than 1/2. But 1/2 to the number of players and 1/2, that's quite a broad gap in terms of the possible probabilities here. So, and you can do this with Q colors, of course, also, and then you get 1/Q here instead. And what you can do here is that you can do much, much better than 1/2. And the simple general strategy that works is that interpret red and green as 0 and 1, and guess that your own color is the sum of the colors modulo 2. If you follow this strategy, then we will be correct if the total sum is even. And then everybody will be correct. And we will be wrong if the total sum is odd. So we're betting essentially here on an event which can actually only have 2 outcomes. The total sum can be even or odd, they both have the same probability. So we will win with probability 1/2, no matter how many players we have. At least as long as we have a finite number of players. If you go to an infinite version of this, then it begins to depend on, well, which version of choice you're using and all other kinds of axiomatic annoyingness. But so you can do much, much better here, even though you can't actually influence the probability that any single player is correct. The thing that you shift around is whether you are correct or wrong at the same time or not. So if you just guess completely randomly, then typically all the time about half the players are correct and half of them are wrong. Here we switch to a situation where either everyone is right or everyone is wrong. And that happens with 50% chance if we now have 2 colors here. And that was essentially this game played on a graph which is complete. So you can introduce a graph here where the players sit on the vertices and everyone sees, well, your neighbors in this graph. And you can do this with directed graphs also, but they'll stay with the undirected situation now. So then the question becomes, if you have a graph here, G here now, which is not complete, how large can you actually make the winning probability? And now this becomes something that's more of a property of the graph here. And what you can show here is that, well, if you take a collection of players which form an independent set, then each one of them has no information about their own hat color. They also have no information about the other players in the independent set. So that the probability that just that little group of players is going to be correct is going to be 1/2 to power size of the independent set. So 1/2 raised to the power of alpha of G is going to be an upper bound for the winning probability here. The other thing which is maybe, well, it's not that hard to see once you actually realize this, is that 1/2 to power the chromatic number of the complement of G is also a working strategy here. And why is that then? Well, the chromatic number of the complement of your graph, that's the same thing as the smallest number of cliques you can partition the vertex set of your graph into. And if you have a partition into cliques, then you can play the modulo strategy that I just described on each of the cliques independently. Everyone inside one of those cliques just ignore everyone outside of the clique. So then you get 1/2 to power the number of cliques. The number of cliques is the chromatic number of the complement of our graph. So the clique cover number instead. So we have some non-trivial upper and lower bounds on this winning probability. So P win here is going to be, I'll just use that to denote that the winning probability for an optimal strategy here now. And then Søren Riis here, he introduced what's called the guessing number, which is n plus the base q logarithm of the winning probability here. And that's called the guessing number. This is something that has varied a little bit in papers on this, whether you take n plus the logarithm of the winning probability or just the logarithm of the winning probability as the guessing number, but it doesn't really matter much which of the two definitions you use as long as you're consistent here. And the reason for having a Q there is that the exact number here that can depend on the number of colors also. So in this, my first paper with Demetres on this, which is, well, a good number of years back now, apart from those bounds, we actually found the correct guessing number for all the perfect graphs. And more generally, where the graphs where the clique number equal the chromatic number. And also we found the optimal answer for odd cycles when Q is large, and complements of odd cycles, and for small graphs in general. We just sort of worked through some cases. Once you removed perfect graphs and you stay with small graphs, you don't have that many things to check. And we found that in general, this is actually squeezed in between not just n minus n over the clique number, which is a bound on the fractional chromatic number. Well, it's a bound on the chromatic number of the complement, but you can use the fractional chromatic number instead of the chromatic number here. Let's see if I've written that correctly. Yeah. And we conjectured that the optimum was going to be given in terms of the fractional chromatic number of the complement. We didn't find any examples where this wasn't true, and yes, we weren't that certain about this conjecture being true, but we were sort of in the position where we thought that this is either true or it's going to be false for an interesting reason. And felt that that was good enough reason to make a conjecture and kick other people into trying to either prove or disprove what we have found so far. And Demetres, so he was a postdoc here in Umeå with me, and after that he started as a postdoc at Queen Mary University in London with Søren Riis. And he, Peter Cameron, and a couple of other co-authors a couple of years ago showed that this conjecture is wrong. And they had been investigating it in general, and they had proven using computer aid that conjecture held for lots and lots of small graphs. And in the end, they actually found a counterexample. And it turned out that the methods that we have been using, which was mostly sort of information theoretical, using entropy inequalities together with fractional clique covers, you couldn't actually prove that the counterexample was a counterexample using those methods. The bounds, just upper and lower bounds, just couldn't be made to match up. But using some more modern non-Shannon type entropy inequalities, they could actually then separate in the guessing number from the bound given by the fractional chromatic number. And we could get it to separate by, in some sense, roughly as little as possible, but they did separate it. So they actually disproved this conjecture. And then that made things more interesting, because then the question is, if it's not the fractional chromatic number of the complement which gives you a guessing strategy which, well, just like the chromatic number of the complement, the strategy that you get from the fractional chromatic number is something rather visible. It's still based on click covers, really. It's just that you don't just do a click cover of the graph, you use a blow up in a sense here. So the question is sort of what really controls this guessing number? And at one of the BCCs, so there should be the BCC, right, the British Combinatorial Conference, right before the pandemic came around, we started discussing this well, a coffee break really, and because we thought that, well, okay, our conjecture was wrong, but the gap that him and then later Riis together with Peter Cameron and another co-author, they had shown a slightly larger gap, not just a constant difference there, but something that depended on n, the number of vertices as well. So you'd be curious about how bad can our conjectured bound actually get? Where does the how much can you sort of push yourself away from the fractional chromatic number up towards the independence number here? So this turns out to actually then connect to the rank properties of graphs. And in our case, it led us to thinking about the random graphs. So why rank properties here? Well, I mean, we know that a graph has an adjacency matrix, and the rank of a graph that is quite simply the rank of that adjacency matrix. So it's sort of a linear algebraic property of a graph. And that's not quite what we need in this context. So we need something called the mean rank. It stands for minimum rank. And so the minimum rank here of a graph, that's the smallest rank among all matrices, which you can build from the adjacency matrix by placing ones down the diagonal in A. And then you can freely modify each non-zero value in the adjacency matrix to whatever you like. And you do this typically over some field, and the mean rank in general is field dependent. So you can either do this over, say, the reals or the complex numbers or over a finite field. And why is it natural to look at this? Well, let's say that the strategy that we had for a clique, that's an example of a linear strategy. We took the sum of the hat value or the color on all the things that we saw. And we guessed that our sum, that our own color was equal to that modulo 2. So that's more generally than an example of a linear strategy. So we could in general have that, okay, player I guesses that color xi is equal to a linear combination of values which that player can see. So that's the same thing as saying that the vector x of hat values here now of colors is equal to a matrix M times the x vector. And that matrix is going to come from the adjacent matrix here because we can only see adjacent values. And this then corresponds to looking at the matrix M prime, which we get by taking identity matrix times x and subtract M here. So M prime will then be a matrix which has ones on the diagonal, 0 for every non-edges, and something wherever an edge was present. And all these sums are now done. If we have, say, Q colors, then we will do this in GFQ. So then we're curious here, why do we care then about the mean rank? Well, if M prime here has rank K, then we only need to assume that the K linear relations actually hold for the random hat values that we have got in order to be able to correctly build up all these values here. So if we have here M prime has rank K, then we're going to get a probability which is just determined by K. But we need to know something about how small we can make the rank of this M prime matrix. And as we had seen before, when we had studied perfect graphs and things like that, so most nice graphs, they actually behave just like our incorrect conjecture suggested. And then, well, if you've been working in graph theory for a while and you discover that sort of nicely structured graphs don't do what you want to do, then you begin to think about, well, maybe this is a little bit like Ramsey numbers or something like that. So let's look at random graphs then. So we can always look here then at this value for, well, this is essentially what I said, that this value in general is going to give you something that's better than this fractional chromatic bound. But the question is, how much can we actually separate it from that? And that's where we started to think then about the Erdős-Renyi random graphs. And in particular for, say, a constant value edge probability P. So now we have a linear algebraic question about random graphs here. And in this case, both the click number and the independence number here is going to be ordo log n here. There are going to be constants involved which depend on p, but as long as p is constant, yeah, then it's only constants here which differ. So the bounds that we're going to have for the guessing number here, they're going to be of the forms n minus n over log n, because it turns out that that's both roughly what the chromatic number of the complement is and what the fractional chromatic number of the complement is. Those are n over log n, really. And then n minus log n, and that's coming just from alpha. So what about the mean rank? Now we could always hope that this is another problem where random graphs are great and give us something non-intuitive that's tricky to construct. And it turned out that just independently and for completely other reasons, same time roughly, a little bit before I and Demetres sat down in a cafe, Alon and co-authors had actually looked at this question. And they connected it more to some geometric problems here. And they actually then proved that independently on which field you're using, there's going to be field-dependent constants here, but the mean rank is n over log n, essentially. if p is constant now. We actually have a log 1 over p in this bound, so if we begin to make p small, then you're going to get something more happening here. And of course, this is a great theorem, but it's awful for us, because n over log n, then that's going to be basically the same thing as the bound coming from the fractional chromatic number. So for this property, random graphs are not good. Random graphs are, well, up to sort of error terms behaving like perfect graphs here. They're not doing anything particularly unexpected. They give you something that roughly corresponds to what you get from following this click partition strategy. But of course, we were interested in, could we actually find some graphs that pushes over towards the bound given by the independence number instead. So this is no use at all for us. But can we do better here? And the answer is that yes, we just need to build better random graphs than this. So the random graphs didn't at all do what we wanted it to. And we also started to realize that, well, it's annoying to actually analyze the mean rank of a lot of random graph constructions, because it gets tricky to actually figure out an optimal way of constructing, well, of figuring out, well, of setting weights in the matrices so that you get a small rank. But what you can do it the other way around. Why not more or less specify the rank from the start and then build a random graph that fits that purpose? So we came up with something looking a bit like this, and I hope it's visible. I need to think I will, there. Move your faces out of my slides a little bit. There, now I can see what I'm talking about again. So we're going to build a matrix B, which is not going to quite be the adjacency matrix, but almost. So we have a couple of parameters, P, K, and T here. Let me move myself out of the way also. There, now. So the first line we will start out here and just put a line with all ones in our matrix. And then the next K lines of B, each position will independently contain a 1 with probability P and a 0 with probability 1 minus P. So this is just a K by N rectangular random matrix that we have at the top of our matrix B. And after that, now we have N minus K minus 1 lines left to do something with. And to each line there, we assign a set of T of these top lines. And we want to choose the sets of lines so that all the sets are different. And the union of small, and I'm not going to say exactly what small is here now, because it depends a little bit what more you want to do with this. But the union of any small collection of subsets also doesn't contain all the lines from K to 1. And this third condition, that was actually something that we put into this, and I now think we don't actually need, because thanks to looking through our notes about this again, now when I was preparing the talk, I realized that we had actually done a miscalculation, which made our result worse than it actually is. So this condition 3 is something that I think we should actually remove now. But I need to write everything down to make sure that we were not correct. And then each line is now assigned the sum of the lines in that subset assigned to that line, modulo 2. So that's just going to, in a big funny way, assign each line in the lower part of the matrix a sum of the things from the top rectangle here. And then we do a little bit of tweaking where we say that if any line here now has a 0 on the diagonal, then we add line 1 to it. So what's going to happen is then that every 0 in that line is going to become a 1, and every 1 is going to become a 0 because we do this modulo 2. So thanks to this, we're going to end up in a matrix B which has 1s on the diagonal. And now at the end, and this is almost just an aesthetic thing, we add one line which had a 1 on the diagonal just without step 5, and also happened to have a 0 at position 1. And since this is random, if n is reasonably large, that's going to happen. There's going to be a line like that with high probability. And that's just going to turn the new line 1 into something more random looking than it was before. It's not going to change much else. So this matrix now is something that we're going to use to build an adjacent matrix, where we simply say that, okay, we build an adjacent matrix by adding an edge between two vertices if either position ij or ji in the B matrix is 1. So you can think of the B matrix as a directed graph. And this matrix A is just what you get by making it undirected. And this thing now is, well, the mean rank here. It can't be larger than the rank of B because I can reconstruct B by just setting some things to 0 in A and putting 1s on the diagonal. And then I'm back to B. And B has rank that's with high probability equal to K if n is reasonably large. So it's equal to the rank of that initial rectangular block. Because those, well, depending here now on how large you choose K, of course, and T. But you can do this quite well if you take T and K to be constants times log n, because then we can just pick random subsets of lines in order to build the lower part of our matrix. And if you make P equal to 1/2 in the original B matrix, then we're going to have edge probability about 2/3 in the A matrix graph. And you're going to actually end up having pairwise independent edges in this thing also. And you're going to have more independence than that, because in order for edges to be dependent in this new graph, they're going to first of all need to share some vertex. Otherwise, they're just going to depend on different sets of random variables in the top rectangle. And this is going to mean that using, well, you're going to have a little bit of potentially dependent things here, since if you pick random edges, well, random collections of sets here. But you can use the Jansson inequality to handle this and see that this thing basically behaves like an ordinary Erdős-Renyi random graph when it comes to things like independence number and click number. But the rank is something totally different. the rank is of the form constant times log n, or the mean rank is. So this is going to give something which has a mean rank which is roughly, well, up to a constant factor the same as the independence number here. So this is going to get, and the click number is going to be about log n for this thing, just like Erdős Renyi. So here, instead of being up at around the fractional chromatic bound like the Erdős Renyi random graph was, this thing is going to be pushed towards the end where you have the independence number instead. And I'm not going to go through the probabilistic calculations here at the end, but it pretty much you use these sort of birthday problem to find the right ratio between T and K in order to make things nice. And then you use Jansson inequality to do the probability estimates that you would like, and apart from that, it's basically the Renyi proof for the independence number that works out nicely here. So, that should be 2/3, not 3/4. So if we choose the constants in the previous slide correctly here now, then you do get something that has roughly the same independence number and click number as Gn 2/3, but we now have a big O log n mean rank. So this essentially more or less gives us optimal counter examples to our own original incorrect conjecture. So, well, if you have an incorrect conjecture, then you should at least make sure that you have the best counter examples to your own conjecture. And getting it much better than this is going to be hard. So another thing that's nice about this new random graph that we built is that it has the right amount of 4 cycles for being a GNP graph. So it's going to be quasi-random. So in terms of graphons, it's going to converge to the same thing as Erdős Renyi. So this thing is going to be, it's doing a good job of pretending to be the Erdős Renyi random graph while at the same time having a whole lot of linear dependencies hidden among its adjacencies. And that's really the main thing I wanted to talk about. Let's see, I was probably going a bit fast here now, I'm seeing, so that I'm ending a little bit quicker than I thought because I haven't had any questions. So I'll actually stop there and see if there's any questions instead.
Thank you. So yeah, are there any questions for Klas?
See something in the chat. It was either amazingly pedagogical and everybody understood exactly everything, or I managed to confuse everyone along the way.
I'll ask a question.
Yep.
So I was going to ask at the beginning if the hat colors are chosen uniformly at random, but I could figure out from your discussion that you were choosing them at random. Does the game become less interesting or more interesting if the hat choices are adversarial? The color choices are adversarial.
Well, the question is what that would actually mean here, because I mean, all the hat choices are made before any of the guesses are made in this game. So
the person choosing the hat colors could maybe they don't know the strategy, but they know the graph, and they could make some choice that's very difficult for the players to discern.
yeah, I mean, if they know the strategy, then of course they can make sure that the players always fail. Because if you know the strategy, then you know the underlying deterministic events that the strategy assumes to be true. Because all of these strategies are really based on saying that, okay, we assume that a small number of deterministic relationships hold. And as long as they hold, we can correctly reconstruct our hat values. And if someone knew what those events were, then they could always make sure to choose otherwise there, just choose so that random values, so that those, well, one of those deterministic relationships fail.
What if
But
they
at the
only
same
know
time,
they know the graph, but not the strategy?
yeah. But if, for example, the players also knew that, then they could, well, in advance, just flip a coin and not tell the adversarial game leader which strategy they had chosen. But without coordination in advance, the probabilities here just immediately drop down to random and really, really low. So this is it's all about creating correlations here, really. So it's the whole thing is fragile in that sense. So it's also something here where one can easily show that you can never do better by going sort of in a more game theoretic direction and using a non-deterministic strategies. The optimal strategies here in sort of a game theoretic sense is always going to be pure strategies. And one of the things that I and Demetres showed early on here is that you can really analyze this game in terms of that there is sort of a code graph connected to all of this, where the optimal strategy really corresponds to determining the maximum independent sets of that graph. So for some of these things, which our general methods couldn't really work for, well, didn't work for, like, well, something like C7, for example. There we actually computed the optimum strategy for some small values of Q by really building this graph and then finding the independence number of it. So then it ended up being a sort of a purely computational result. But then later on, other people did sit down and do quite a lot of hard work to figure out the correct independence number, and hence guessing number 4 odd cycles of general lengths and certain values of Q, so the number of colors here.
If there are no more questions, let's thank Klas again.